So looking over the summer assignment, in some cases giving you answers and in some cases giving you some hints as to what you should be looking at. So let's look at number 4. Now as you look at these questions, now I hope you are asking yourself, why is the textbook author, why is the instructor choosing to give you this question? What is it you're supposed to learn from this question? Well, the thing you're supposed to learn from this question is, when you're dealing with mass of different components in a solution, can you add them together? Are masses additive? And the answer is yes. So the correct answer here would be that we're going to get 280 grams. Compare that to B, where we're asking about adding the volume. Now you're probably thinking of this as 100 milliliters of sugar, so now less than a cup of sugar, and you put it into water. Are those volumes going to add? Well, think about this. If you have a container, a couple containers here, and one of these containers is full of something the size of ping pong balls, and the other container is full of something, I'm not drawing them small enough, but something small, tiny and spherical, like maybe BBs. So this is full of BBs. It takes me too much time to draw all of those in. So this is full of BBs. When you pour these together, are the two volumes going to add to twice the volume? Well, I think you'll see that when we pour the BBs in here, they're going to fill up much of this empty space. And the same is true for this solution. Volumes are not additive. We will look at examples in class of where we can put 100 milliliters of one chemical and 100 milliliters of another chemical, and we will come up with 195 milliliters. Volumes are not additive. And actually, we'll look at another example where it's the result of a chemical reaction where we add 100 milliliters of one chemical and 100 milliliters of a second chemical, and we come up with 101.8 or so, 102 milliliters. So volumes, you can't just add them together. So this is going to be, I don't know what you're going to decide is the best answer, but it's going to be one of those. This is a really typical kind of question, and it's really getting at this idea: do students, anyone, understand that these bubbles coming up out of here, that this is just a physical change? We could represent this as being water that's in the container in liquid form. Down here, all this water. We are talking about water, right? Okay. And turning into water as a gas. We still have water in those bubbles. There hasn't been a chemical change. Very commonly misunderstood concept. It's just a physical change. Question 6 is also looking at the idea of physical and chemical changes. So you want to analyze what's going on as this glass rod is held in the flame, and what is happening to the wax and what is happening to the wick of the candle. Make sure you explain each So you need an explanation for each of those objects. Maybe your paper will look something like this. So here we have data. Now to really analyze this data and answer the question, you have to remember, let's see, I've got to look at number 20. We've got to remember that our target is 10.62. That's 10.62 is the accepted value. That's the accepted value. And we see here that this particular set of measurements jump from this low to this really high value, and so they are not precise. Precision indicates that we're using a precise instrument that measures consistently. That would be precision. These are not precise, they're not consistent, and they're inaccurate because they're nowhere close to 10.62. These are very precise. You know, if you think of this as a target, you see that even though the goal here, the accepted value, is 10.62, these measurements are grouped very closely together, even though they're incorrect. So they're precise, they're grouped very closely together, but either the operator error, something happened consistently to make them read too small, or the instrument itself is calibrated incorrectly. So these are precise but not accurate. These are precise and accurate. They only vary in the last significant digit. That is what makes them precise. And they are accurate because they're really only only vary from the accepted value in that last significant digit. As you're making these graphs, I'm going to encourage you to make the graph with Excel or some other graphing program. If you need to get information about where you can find those graphing programs online for free, be sure and email me and I'll let you know about that. You should include the graph, whether it's done with Excel or done by hand, in your homework, and you should include the equation for the line that you've drawn. Now what you'll see here is that we have here, this is Fahrenheit temperature versus Celsius, and here you'll see at 100 degrees Celsius, if you kind of come up here and look, we're probably around 212. That's the boiling point in Celsius and the boiling point in Fahrenheit. And of course the boiling point is the freezing point of water in Celsius is 0, and here we're somewhere around 32. But the other thing you want to be sure and notice is the slope of this line. Remember the line equation, y equals mx plus b. This line equation is the conversion factor to convert from Celsius to Fahrenheit. If you take temperature Celsius and you multiply it by 9/5, which is the same as 1.8, and you add 32, you'll have the temperature in Fahrenheit. And as we go through this course, we're going to see more and more the line function of this graph is going to tell us some important, useful, and interesting information. And be sure you take a look at that. And I believe there's more to 23 as well, to make a graph for maybe Celsius and Kelvin, but you need to look at that and see what the rest of the assignment is. Question number 31 deals with sig figs and addition. And you can take a quick look at those answers and see this is the answer before rounding and then the answer after rounding. And C, D, and E are here. Take a look at those. (37B) was not in your assignment, but we're going to take a quick look at it here in case you decide you want to. Some converting within from metric to English system, which we really won't do very much in the class, but just another way of taking a look at how many sig figs you should use. Looking here at problem number 49, which is a really interesting problem. It deals with this idea of a range. Like you might have a range of weights, so that's going to give you a range of dosage when you talk about the milligram per kilogram of acetaminophen in some kind of cough syrup or something here. So first thing you want to do is convert the dosage to milligrams. We have it in teaspoons, but we need it in milligrams. So the dimensional analysis would look like this. And another thing we need to do is we need to get the range of body weights in terms of kilograms. So we're going to convert pounds of child to kilograms of child. And we have a range. It goes from 24 pounds up to 35 pounds. And so we have this range from the low value to the high value. That's our range. And so if you combine those two things to look at the range of weights, we can see here by using dimensional analysis what factors out, and that leaves us with milligrams of acetaminophen per kilogram of body weight for the kids. And so our range is just going to be from this number to this number. So that's how the dimensional analysis works out for problem number 48. For problem number 60, now don't forget, you need to be including in your problems these 5 things. The units, be sure you're careful with the units, just like we were in this last problem. Be careful with your units. Be sure you put your data, the things you know and the things you don't know. Now in problem 60, the things you know are that you have 11.2 milliliters of water, and you know that you have 5.25 grams of silver, and you know the density of the silver, and the unknown is the total volume. So make sure you have that data listed. Make sure you show any relationships you might use. Like in this case, you're going to have a bunch of units that are your relationships. Just like back here, our relationships were these units and numbers in the problem. And substitution, we've called that things like substituting in the correct values here. In other words, 1 pound, we substituted a 1 into this relationship, and 0.4536 into this relationship between kilograms and pounds. And then the final solution, and make sure your final solution has the correct number of sig figs or significant digits. Don't forget those. Problem 66. Remember, sketch what you know. Remember relationships like density equals mass divided by volume, and remember things like, well, you've got this, if you you have a cylinder, you can find the volume of the cylinder. How do you find that volume of that cylinder? There's an equation you should know that will help you with that. Big thing here, patience and persistence. Patience and persistence. Keep at this problem until you have solved it. Excellent.